Hello everyone, my name is Margaret Pinson. I'm a PhD student at the Ghent University, and I will present some of my latest results of my PhD with the title Hydrogen Trapping and Embrittlement Revealed in Martensitic Iron Aluminium Carbon Alloys. So how does this presentation look like? Well, I will start with a small introduction, then I will tell you something about the hydrogen embrittlement mechanism in simplified martensitic iron carbon steels, and then I will suggest a way to increase the hydrogen embrittlement resistance by adding aluminium, and I will end, of course, with the most important conclusions. So first, a small introduction. So how do martensitic steels look like? I suggest most of you already know that, but it's in fact a quite complicated microstructure. You have a parasitic grain. This can be subdivided into martensitic packets, which can on their turn be subdivided into martensitic blocks, which also consist out of martensitic lads. All these specific substructures have specific boundaries. We have high-angle grain boundaries, which contain the parasitic grain boundaries, the packet boundaries, the block boundaries, and the lads are surrounded by low-angle grain boundaries. These very complicated structures hinder, in fact, the complete understanding of the hydrogen embrittlement mechanism. Moreover, it also has a high amount of influencing factors, such as carbides, precipitates, second phases, segregations, and so on. And therefore, during my PhD, I used generic iron carbon steels with a simplified structure to get more fundamental insights on the interaction between hydrogen and martensitic steels. However, another important challenge I endured during my PhD is that high carbon martensitic steels are way too brittle to be tested by the traditional in situ tensile testing. Therefore, the hydrogen embrittlement mechanism of brittle materials are often not correctly evaluated, and therefore I developed a new methodology, namely an in situ bending rig for brittle materials. These bending curves can be performed in air or with simultaneous hydrogen charging, this is called in situ, or even after saturation inside this bending rig setup and then tested. This is a saturated in situ tensile test. A simplified representation of the setup is also given in this figure. So how does the hydrogen embrittlement of martensitic iron carbon steels look like? Well, I worked with 3 alloys. So these are simplified iron carbon martensitic steels with 0.2, 0.4, and 1.1 weight percentage of carbon. The generic properties are also given in this presentation. So the 0.2 and 0.4 carbon steel have a very similar parasitic grain size of about 30 micrometers. And the 1.1 has a much higher parasitic grain size. This is because it has a very high critical cooling rate, and thus it had to be heat treated at higher temperatures to obtain a fully martensitic structure upon quenching. I say fully martensitic, which is in fact not entirely true, because it also has a high amount of retained austenite. The hardness increases with increasing carbon content due to carbon in solid solution, which is generally accepted. The high amount of retained austenite is something special in this 1.1 carbon steel, but we also have a high amount of quench cracks due to its very brittle character. The interaction between retained austenite and quench cracks with hydrogen is studied in depth in this study. I will not go into detail about this now, but if you want to have more information, you can always look at this paper. So first, before I do the mechanical testing, I see where hydrogen is trapped inside these materials. This is an example of a TDS curve of an iron 0.4 carbon steel, and we see that there are 2 main trapping sites, namely the high-angle grain boundaries and the dislocations. This is investigated by comparing the activation energy with activations energies found in literature, and also by applying several heat treatments to see how these trapping sites change. And we can quite surely say that these are the high-angle grain boundaries and dislocations. There's also a small amount of hydrogen trapped at lattice positions, but this can be ignored for the rest of this presentation because the value is very low. Here is some sort of summary of where hydrogen is trapped and how much hydrogen is trapped at the trapping sites. The amount of hydrogen trapped at the trapping sites is calculated as the area underneath the Gaussian curves, which correspond with that specific trapping site. So what do we see? Well, the amount of hydrogen trapped at these locations increases with increasing carbon content. This is, of course, because carbon in solid solution induces more dislocations, so we have more available dislocations as trapping sites. The amount of hydrogen trapped at the high-angle grain boundaries mainly depends on the parasitic grain size. The higher the parasitic grain size, the less hydrogen can be trapped there. This is because the amount of high-angle grain boundaries is inversely proportional with the parasitic grain size. So now we know where hydrogen is trapped in this type of steels, and we can look at the mechanical behavior. So these are the fracture surfaces which are obtained after bending tests in air. So with 0.2 weight percentage of carbon, we have a fracture surface which mainly consists out of microvoids. For the 0.4 carbon steel, we have a mixed fracture surface. We have some intergranular features, microvoids, and cleavage facets. So it's really a type of mixture. And for the 1.1 carbon steel, we have a purely intergranular fracture surface. Now, it's interesting what happens when we charge these with hydrogen, we saturate them, and then do the bending testing in situ. Well, what happens, we see for all three materials, so although they had a very different behavior in air, they all have a transition to a cleavage type of fracture. So we can state for these simplified iron-carbon steels that hydrogen causes a transition to a cleavage type of fracture. So hydrogen embrittles in a specific way for all these three types of steel, independent of the carbon content. To investigate this in more detail, I also looked at the cracks which are formed on the ND surface at the tensile site of this bending specimen. And what we see, this is an example for one material, but we saw this for all three materials, is in air we have a mainly fracture propagation path along the parasitic grains. But when we charge it with hydrogen, there's a transition, and we see really cracks appearing along the martensitic blocks and along the martensitic packets. So hydrogen, in fact, embrittles the martensitic packets and blocks. And thus, the resulting cleavage type of fracture really originates from the Heady mechanism. So we have decohesion of our martensitic blocks and packet boundaries. So what can we conclude? Well, the martensitic blocks and packets are really the weakest link in martensitic structures. So as a second part, I will propose to you now how can we limit the hydrogen embrittlement behavior of these martensitic steels. One way to do so, which is most commonly described in literature, is to introduce deep trapping sites. By introducing deep trapping sites, we can avoid the hydrogen accumulation at the martensitic blocks and packets. So this is very beneficial. However, this also requires a high amount of alloying elements and complicated heat treatments. This increases the price, which is not always a valuable option. A second way to do so is by introducing a more ductile phase. This is an example of, this is an example of Professor Koyama, and he showed that, in fact, ferrite has a high crack arresting ability. So by introducing a more ductile phase, we can really limit the crack propagation in this type of steels. However, martensitic steels are mostly used because they have a very high hardness, very high strength, and introducing a more ductile phase can really reduce the hardness. So the idea of my PhD was really to introduce very, very small amounts of ferrite to limit the decrease in hardness, but increase the mechanical behavior. How did I do that? Well, by introducing already a very small amount of aluminum, you can really enhance the ferrite formation. There's a bit of shift in the slides I see, but no worries. So this is an example of a 0.4 carbon steel, and by adding already 2 weight percentage of aluminum, we really enhance the ferrite formation kinetics. And the nice thing about this is that we can already form ferrite just by a very simple quenching treatment. This is in fact very peculiar because normally ferrite is introduced by a more complicated heat treatment, but just by adding aluminum, you can really form ferrite just by simple quenching. How does the microstructure look then? Well, you can see here, so we have a martensitic grains, but along these martensitic grains, so on the parasitic grain boundaries, we really form this very, very small ferritic layer. A more detailed characterization by TEM, so we made FIP samples with TEM that contained this microfilm, and what we see there is it really has a really clear BCC structure, and moreover it also has a carbon depletion. Why does it have a carbon depletion? Well, if you quench your austenitized steel, the first thing you form are this ferrite formation, and parasitic grain boundaries are mostly the nucleation sites for phase transformation. So, and since the carbon solubility in ferrite is much lower than the surrounding austenite, your carbon is pushed out. So this also results in carbon depletion. Now, the most interesting part is, of course, now to see what the effect of this ferritic microfilm is on the mechanical behavior. So I first did bending tests in air. So the red curves correspond with the iron carbon steel without aluminium, and we really see a limited amount of ductility. This is a bit different than the things I showed before, but this is because both alloys were quenched from the same high austenitization temperature to really avoid the effect of the austenitization temperature. Same results were obtained just by comparing the iron 0.4 carbon steel as I showed before, but just since limited time, I only showed this result. But so it really breaks very soon without this ferritic microfilm, and when we add aluminium and we create this ferritic microfilm, we really can sustain much, much higher extension values than without this aluminium microfilm. We can also see this in the fracture surface. So without aluminium, we have a purely intergranular fracture surface, but when we add aluminium, you really can see microvoids on top of these intergranular features, and this really indicates that fracture occurs along this ferritic microfilm. The yield strength of ferrite is much lower than martensite, so it really is the carrier of the plastic deformation. So in fact, it acts as a kind of glue and holds your martensitic structure together. You can also see that the hardness values are very similar. So we introduced ferrite, but we didn't influence the hardness, which is very good. Yeah. And then it's of course interesting what happens if we also add aluminium, when we also add hydrogen, of course. Well, as I showed before, without aluminium, we really have this transition to a cleavage type of fracture by the Heady mechanism. But if we add aluminium, you can see we can sustain much larger extension values than without aluminium. And we can also see a completely different fracture behavior. So with this ferritic microfilm, we really have a transition with hydrogen to an intergranular fracture path. How does this come? Well, this in fact comes by an interplay of the Heady and the Help mechanism, where we really have decohesion of our martensitic and ferritic martensite-ferrite interface. So the microfilm can extend the extension in mechanical loading in a hydrogen-rich environment just by redirecting our crack propagation path along this interface and away from this weakest link, which are the packet and block boundaries. So I can go over the conclusions. So I did a fundamental study of the hydrogen trapping behavior in generic iron carbon steels, and I saw that hydrogen is mainly trapped at the angle grain boundaries and the dislocations. When these type of steels are mechanically tested in a hydrogen-rich environment, hydrogen will cause a transition to a cleavage type of fracture, which can be linked to the Heady mechanism, and the resistance of these type of steels can be increased by introducing a ferritic microfilm on the periostic grain boundaries, which does not influence the bulk hardness, but it redirects the hydrogen-assisted crack propagation along the periostic grain boundaries and away from the weakest link, which are this packet